Okay, so this is the last lecture, and before moving into the testing hypothesis, I would like to do a little bit of recap. So always to put it in context and see how the flow of the lecture is done. So what we've done so far, two lecture on testing hypotheses. Again, testing hypotheses as part of statistical inference. What does statistical inference mean? It means that I want to test a certain hypothesis or a research question about the population. But in order to do so, I take a sample, I collect data on that sample, and I test whether whatever question I have or whatever hypothesis is true or not true. I reject or I fail to reject. And in which form do I do test of hypothesis? So there's a test of hypothesis with one sample. What does it mean? It means that I want to test something about one population, such as I would like to see whether, let's say, the body mass index in among EUB population is greater than 25 kilogram per meter square. And this is for continuous. Or I would like to know or check the claim that the population of Lebanon have more than 50% are smoker. So I'm only talking about one population, student or the population of Lebanon. So what I do, I take a sample of EUB student, check their BMI, and do the test. And I have two tests, two ways of doing the test. If the n is greater than 30, I test it with the z equal x bar minus mu 0 over s over square root of n. So my hypothesis is h0 mu equal mu 0, which is the value I'm testing, like 25 kilogram per meter square for BMI. And H1 is mu is maybe greater than mu 0, which is greater than 25. So it depends on the sample size. So if n is more than 30, I use the z, I use this test. By the way, I will post the a sheet of all formula that you will need on Moodle. So I use z, and if n is less than 30, I use t. Again, always what I'm doing, I take a sample, I find the mean of the sample, I compare the mean to my mu 0, which is 25, and I divide by the standard error of x bar, standard error of x bar, and I get a number. That number, I compare it to a critical value. If my variable is dichotomous, and I'm checking whether, again, H0 mu with p, the proportion of for instance smoking is greater is equal to 0.5, which is 50%, or HAP is greater or equal to 0.5. Okay, so again, that's probability, that's a variable that's dichotomous. It's smoking, not smoking, like depressed, not depressed, diabetic, not diabetic. Again, first of all, I check whether all my product of the sample size times the probability P0. So P0 is 0.5. So I would look at all this n times 0.5, n times 0.5, because this is Q. If it's all greater than 5, then this is my test of statistics, and I do my test of statistics and then compare that Z to a critical Z. So one sample, meaning that I'm interested in one population, university student or adult in Lebanon. I take one sample. So I take one sample, I calculate the mean, or I calculate a proportion and test the hypothesis. Another test of hypothesis is when I have two samples. So I'm testing hypothesis about two populations. Sorry, I forgot here to put two populations. So when I'm comparing two populations, and my outcome is continuous, meaning that my outcome is the variable I'm interested in is continuous, like body mass index, weight, height, and I'm interested in looking whether two groups are different. What do I mean by two groups are different? It means that a variable such as gender, displacement, or place of residence, which are comprised of two groups, their means is different. So the mean body mass index between male is different than that of female. The mean cholesterol or depression score among those who are displaced is different than the mean depression score among those who are not displaced. Okay, so therefore, my H0 in that case is mu1 equal to mu2. HA is mu1 different than mu2. Recall that we can put different, depends on how I'm stating the hypothesis. So are displaced have different depression score than non-displaced, or I can state it as are displaced people have a mean score of in depression greater than those who are not displaced. Okay, mu1, mu2. And therefore, my test of significance is the same. It's x bar 1 minus x bar 2. So I find the x bar for the male, for instance, or for the displaced, the x bar 2 for the non-displaced, and my test of statistics are x bar 1 minus x bar 2 over the pooled standard deviation square root of 1 over n1 plus 1 over n2. Recall that we check whether I can pool the variances. So I would look at squaring the variances and do the ratio, and if the ratio of the variances is between 0.5 and 0.9, I guess, then I can do the pool. So what's the difference between Z and T is also whether the N, your N, both of them are greater than 30 or at least one of them is less than 30, you use the T. So this is again for a recap when you are testing with two independent samples. What does this mean? Meaning that you are comparing two groups. You are comparing the BMI between male and female. You are comparing depression between those who are displaced, non-displaced. You are comparing cholesterol between those who reside in urban area versus rural area. So that we took, if you recall, right? Now, what we took as well is when we test hypothesis with two dependent samples. What this means, we said two dependent sample is again, let's say we have group 1, we measure their depression score, we do an intervention, and then, so time 1, time 2. So at time 2, so I do the intervention, and then the same group, I take a depression score. So these are not considered, T1, T2 are not considered independent because this is the same person being tested twice. So we call them dependent sample. And this particularly, we took it for continuous variable. Okay, so I was saying that now we're talking about the two dependent sample, and two dependent sample meaning again the same sample being tested before and after, like taking a group with depression score at time 1, do an intervention, and then depression time 2. Okay, and then the test of statistics would be I do the difference between xi1 and xi2. So I do the differences and then I average the differences, and my test of statistics would be x bar minus mu of d equals standard error of d. The hypothesis would be h0 mu of d equals 0. What this means is that under h0 there are no difference between before and after, and h1 would be mu of d. Depends what you are testing, could be greater than 0, less than 0, or could be different than 0. Okay, any questions?
دكتور, just to make sure دايما ال H null بتكون المين equal to the other, and the H1 بنحطها either greater or less or
H null is H null, meaning that no association, no difference. Okay, no association meaning the means are different, are the same between x bar 1, between group 1 and group 2. It means the proportion is equal between group 1 and group 2. And if we're talking about dependent sum, it means that there are no difference between time 1, for instance, and time 2. Now the H1, how do we decide more than 0, less than 0, or different than 0? It depends on your hypothesis. Now the new scenario. So we've done differences between, so one testing one sample, testing two sample for continuous, testing two sample, the independent sample for the dichotomous variable, and testing two dependent sample when the outcome is continuous. So what was left is testing hypothesis with two independent sample, but the outcome is continuous. And then we have two independent, an independent variable like male and female. Okay, so now we're back to the new scenario where I have my outcome is dichotomous, and I'm comparing this dichotomous between two groups. For instance, I would like to see if there is a difference between male and female with respect to result of a surgery, or if I have difference in obesity, with cancer remission or result of a surgery between those who are obese or not. So on each participant, we identify the group, we measure the outcome. Okay, so I think I have whatever. Okay, so for each participant, I identify the group, measure the outcome, and what I will have is I will have an N1, an N2, a P1, and a P2 for every sample. So again, my H0 would be P1 equal P2 in the population, and my H1 is P1 different than P2 or P1 greater than P2 or less than P2. And we call them, these are called one-sided test, and this is two-sided test. Okay, so how to do it? So again, dichotomous outcome and two independent sample, P1, P2, and then the test statistics similar to what we did for one proportion. If you recall, one proportion, P equal P0, P different than P0. The X would be, the Z was P hat minus P0 over standard error of PQ over N. Now we are looking at P1 equal, we have two P's. We check if all the product of N1, P1, and 2 P2, N1, and 2 P2, and 2 Q2, all are greater than 5. And then the test statistics would be P1 minus P2 over the standard error of P1 of PQ, P0, not P0. I think this is the P average. I'll check it out. And I'll check all this out, okay, for you to see how it is on the screen. Okay, so this is the example. So it's the prevalence of CVD difference in smoker as compared to non-smoker in the Framingham offspring. So what is it that we need here before we go to the second handout slide?
Do you mean like we need like N1, P1, N2,
So,
P2?
okay, great. So what are we comparing? Oops, sorry. Okay, what's my outcome?
So non-smokers and current smokers?
Outcome. So the question is prevalence of CVD different in smoker as compared to non-smoker. What are the two groups I'm interested in, or the two populations?
Oh, okay. So free of CVD and then history of CVD.
No, what are the group I'm interested in comparing?
Comparing smoking
and non-smokers.
So smoking is my independent. As independent. So I have smokers and non-smoker. Okay, now what am I interested in comparing in those smoker and non-smoker?
CVD.
What exactly? CVD, definitely. CVD is my outcome. CVD is outcome.
The prevalence?
Prevalence, yes. Okay. So CVD comes as yes or no, right? So what is it that I'm comparing? probability of CVD, the prevalence of CVD among smoker compared to prevalence of CVD among non-smoker. How do I get them in the table? And what's my N in the table? So I have two groups, smokers and non-smoker. So what's my N1 of non-smoker?
Non-smoker,
Yes.
3055.
So this is N1. Okay. What's the prevalence of current smoker? What's the N of non-current smoker? So this is N1 and this is N2. And
Yeah.
it could be N1, N2, and it could be my current smoker as N1 and non-smoker as N2. It's fine, irrespective. Okay. So now, we got two populations, smoker, non-smoker. I collect the data and I find that among the non-smoker, 2,757 have CVD, don't have CVD, and 298 have CVD. What is it that I'm interested in?
History of CVD, since we're measuring the prevalence.
Okay, great, Reem. Okay, so I want probability of CVD. Is everyone is okay? So I want
Yes.
the percent, which is 298 over 3055. So this is the P1, and P2 would be 81 over 744. Did you get me? So what we are comparing are what is the probability of history of CVD among non-smoker compared to history of CVD among smoker. It could be anyway. You could put current as N1 and non-smoker as N2. But irrespective, your two population are smoker, non-smoker, and your outcome is prevalence of CVD. CVD comes with a yes and no. The probability of CVD is the number who have CVD over the total number. Okay. So test of a, so this is what we want to do. We want to test whether P1 equal P2, and the example smoker equal non-smoker in terms of CVD. And since the way that it was stated is, are they different? So now we are at the testing hypothesis.
Just a moment before we move on, Professor, I have a question.
Yes.
So I was just lagging a little bit while you were explaining the first part of the question. We're interested in only the people with the history of CVD comparing smokers with non-smokers, right?
And yes, the question is the prevalence of CVD different in smoker as compared to non-smoker? So usually any variable, it has a yes and a no, right? But
Right.
when I ask you to report on the proportion with a certain outcome, you would take only those with yes, right? So it's the 298 over 3055. And usually you don't report the history, no CVD, you don't report those with free CVD, you report or you work on the probability of having CVD. That is, we are comparing whether the prevalence of CVD is different between smoker and non-smoker. If we were interested in whether people free of CVD, probability who are free of CVD is different, we would have taken the 2,700 over the total. But what we are interested in, probability of having CVD, whether it is different between smoker and non-smoker. So therefore, it's a prevalence of having CVD. And we were talking about, when we state the hypothesis, is that we were looking at only different. We didn't say, is the prevalence of CVD greater in smoker compared to non-smoker? We only stated, or the researcher stated, whether it's different. And therefore, when the hypothesis is stated, it's P1 equal to P2 always. This is the null. But the alternative or the research hypothesis is H1 P1 equal P2 because it stayed different. So this is what we call two-sided test. Two-sided. Okay, so it doesn't matter whether it is less or more. It's just different than P1, different than P2, with an alpha 0.05. Remember, always we state what's my alpha, because I need a critical value under the normal curve. And then my variable would be plus 1 over n1 over 1 over n2. So this is my Z statistics, and the decision rule will be on the Z. This is H0. Okay, my decision rule is alpha 0.05. So any value less that belongs here, falls here, or any value that falls here, 0.05. So will be rejected. So, and we reject the null hypothesis if the calculated Z, the test statistics, falls here or falls there. So if it's Z is less than minus 1.96, or if Z is greater than 1.96, similar to any other statistical test that we've done before. So again, the compute test statistics is Z. Sorry, I apologize. Do you see, you don't see, right, all the signs?
They're not there.
I don't know why we don't see all the signs. Okay. So it's P1 minus P2. This is equal. This is equal. This is equal. And this is plus. So again, the
No
test
worries.
statistics. The test statistics. So we have, again, just not to forget the flow. So we state our hypothesis one. This is the test statistic that we do, and then there is a decision rule that if the test statistics falls within the area under the which is decided based on the alpha 0.05, then we reject H0, and this means that there is a difference in CVD between smoker and non-smoker. So we actually we compute the test of statistics. P1 is non-smoker. So this is non-smoker versus smoker. So this is 81 over 744. Just to remind you, this is your P1. Okay, so they put it as P1, which is fine. 81 over 744. Okay, and then your P2 is 298 over 355. So this is CVD in smoker over N2, which is how many smokers we have. This is CVD in non-smoker, and this is all N1, all non-smokers. So the population of sample of non-smoker, and this is 3055 is the sample of smoker. Now, and this is 10% have CVD among non-smoker compared to almost 9% or come in 10% among the smokers. And then what we do is we take an average again. So the test of statistics is P1 minus P2, whatever we got from the table. And then we have P and Q. Those P and Q are the average of the two P's of P1 and P2, which is 9%, 0.0988. And then I replace by those numbers. So therefore, my Z equal probability of CVD among non-smoker minus probability of CVD among smoker over this. This is all, remember always, it's the difference over the standard error. This is called standard error of P1 minus P2. Okay, so what we do is we take a pool. This is average P, and this is average P1, P minus 1 minus P, and then over 1 over N1 plus 1 over N2. And what we get is 0.927. So what is this 0.927? If we look at the standard normal curve, we said the decision is if we are here. So if we are here, it means reject H0. Here and here is reject H0. And if we're somewhere here, this is accept. So where are we? So we have, what we got is 0.927. This is 0, so this is 0.927. So what's my conclusion? Since this 0.927 is more than 1.96, but less than 1.96, so it happens inside, so therefore we accept H0. So we don't reject H0, we accept H0. This means that there is no difference in CVD between smokers and non-smokers. Okay, there is no difference.
Professor, we didn't do the test statistic of N1, P1, and N1, Q1 is greater than 5. We didn't do
You're
that, right?
We did not do that. Do you know why we did not do that? Because your number are really high. Already you have N1 and N2 really large, but nevertheless, you're absolutely right. We can do them. But when you have large N's, so it's most likely that your N1, P1, N2, Q2 would be greater than 5. But it's definitely something that to do. Thank you, Nasreen. So what Nasreen is saying, we did not do this condition, which is N1, P1, and 2 Q2, and 2 P2 and 2 Q2 all greater than 5. We did not do them because our N actually are large. Okay, but nevertheless, you can do them. So here my N was almost 10%. So 10% out of the 3055 is 300, right? And here I have almost 10%. My 10% is 74, right?
Yeah.
Okay, let me go back. Not go back. I mean, I got a P of 0.10, right? So it's almost 11 or 10%. So 10% times 74 is almost 74. And here the same. And the Q1 would be even more. So this is really met. Yani this assumption is met.
Like immediately,
Nevertheless, you can definitely do
yeah.
it. But usually we don't worry when our N are so large.
Yeah.
Okay. So this is for testing for two proportion, okay? So P1 and P2. This means, again, what does two proportion mean? It means that I have an outcome that's dichotomous, like having diabetes or not, having CVD or not, depressed, yes or no. And I'm looking at those outcomes, comparing two groups. Like two groups could be male and female, obese, non-obese, having other chronic diseases, yes, no, residing urban versus rural, educated, not educated. So you are comparing two groups, but what are you comparing? You're comparing the probability of having the outcome between one group compared to the second group. So you take two samples, N1 and N2, look at how many have CVD, calculate the probability of CVD, and then do the test of statistics, which is P1 minus P2, which is the difference in probability, over the standard error of that difference in probability. The standard error in when you have two population, you average the P's of the two, and then you use it when you calculate the standard error. So here is the average P, which is from the two probabilities, and then it will be the average P times 1 minus P, which is Q, times 1 over N1 plus 1 over N2. Whatever number you get, you compare it to the critical value you have chosen for your alpha 0.05, and then you decide whether to reject H0 or not to reject H0. And when we say not to reject, mean accept H0. And this means concluding is that there is no difference between the two groups, and one, which is the smoker and non-smoker. This is what we got. So now we come to the last, okay. So this is the last scenario where we have hypothesis testing for categorical, but the outcome is ordinal. So for categorical and ordinal outcome. So we have a categorical or ordinal outcome, and meaning that, for instance, what's a categorical outcome? Can you give me an example?
When there is more than one thing to study,
Okay, so
like a list.
it's not a list. The outcome is categorical or ordinal, meaning that the answers are more than 2. Okay, so they could, for instance, depression could be dichotomous, yes, no, right? But it could be as well ordinal, like no, mild depression, moderate depression, and severe. Okay?
Yes, categorically, such as
Okay.
mild
Categorical, yes, categorical would be prognosis of a disease, prognosis. So
Oh, okay.
prognosis, or let's say after an exam, you pass. You conditional pass, conditional, or maybe fail. Okay. It could be 3. So this is the type of, and we can also look at even so what we have is pass, conditional, or fail, or depression, no, mild, moderate, or severe. Okay, so what we are interested in this, the chi-squared, this is a new test that you are going to take, is first considering one sample. Okay, so I can take a sample of student, for instance, and I would say that I expect that 70% pass and 10% conditional, and fail is, so I would say 20 and 10 fail. This is what you expect. Okay, so you expect that 70% would pass the course, 20 would have a conditional pass, and 10 would fail. Or again, if you take a group of people who are exposed to war, you would expect like the majority, 33% would have severe depression, moderate is 33%, mild is maybe 10, so 66, 76, and the remaining would have no depression, like 20, 24. All right. So this being said, if I want to state a hypothesis, I would say if there is no difference, okay, so what I would say is that all the p's would be equal. Okay, either it would be equal, or if I expect that they are 70, 20, 10, it means if I take a sample, those would be equal to the numbers, the percentage that I have put under the H0. So P1 would be equal, for instance, it will be equal to P10, P20, etc. So this is like my data fits the percentages. So we call it like a goodness of fit. So I expect that if I collect a sample of grades, my distribution will fit 70, 20, and 10%. And the HA would be, no, it does not fit. So the test statistics is the summation of what I observe when I collect the data. And then I see the difference from what I would have expected if the distribution is 70, 20, 10, over expected to see the magnitude of the difference. And then I would compare to a critical value. But here the distribution, as we call it, it's not a Z, it's not a T, it's called a chi-square test. A chi-square test is again, it's a probability distribution. It is not a normal distribution, it's a skewed distribution, and it is determined by its degrees of freedom, which is K minus 1, which is the number of category. So here we have 0, 1, 2, 3, 4 categories, minus 1, which is 3. And then the alpha, which is the probability, which is 0.05. I continue, it's not very an easy concept. So this is, so if H0 is true, the chi-square will be usually equal to, and it's towards 0. So this is probability. So this is the probability. These are probability. And the closer to 0, chi-square. So this and these are the chi-square, the chi-square. So, and this is how it looks like. Okay, so is it normal?
No.
No. So what happens is that the larger the chi-square, this value, the larger this value, the larger, we'll say, we will decide what's larger. So the larger this value, the more likely that H0 is not true. It means that there is a difference between what I saw in terms of the distribution of grade and what I would have expected if there is no difference between the expected and the observed. Okay, so I reject F0 if chi-square is greater than the critical, and then I take it from the table. It's not a table, it's table I chi-square. I'll share with you the table of chi-square. I think I have saved one updated version of this presentation, but this is not the one I'm sharing. I will share it in a few minutes. Okay. So the example. Okay, so a university survey reveals that 60% of the students get no regular exercise, 25 exercise sporadically, and 15% exercise regularly. What's the variable I'm looking at? What is the variable I'm looking at?
Exercising.
Exercising. And this exercise has how many exercise?
Three
It's
categories.
three category. It is a kind of ordinal. So no exercise, sporadic, and regular. All right. So what we expect, what a university have seen an earlier survey that those who with no exercise is 0.6, sporadic is 0.25, and regular is 0.15. Okay, so this is expected. Now, what the university did is that they did a health promotion campaign, and they wanted to actually reevaluate, and they want to see whether actually now at this point in time after their campaign, the distribution fits the earlier distribution, which is 60, 25, and 10. So what they've done, they did they did a study on how many 2025 on those. So they got a student, 255 were found to be, so they have a 470, so total 470 student. Okay, they evaluate them based, so they ask them, do you exercise, and if yes, sporadic or regular. So 255 reported, so these are observed. Okay, observed. 255 said they don't exercise. 125 out of the 470 said that I exercise sporadically, and the 90 out of the 470 said that I exercise regularly. So this is what they observed. What would they have? What would have been the expected number of those who would don't exercise sporadically, or 15, if H0 is true? H0 is true, it means that we expect that this probability, this distribution, 60, 25, 15%. So if I expect after the health promotion that 60% of my students don't exercise, so this means my expected would be 0.6 times 470. What do I expect if I have H0 is true? So I expect that out of the 470, 25% they do sporadic, and in the regular, I would have expected 15% out of the 470 who would be regular. So how much are these numbers? Okay, so first, just again to recap, or to put it in terms of the H0. So I expect under null hypothesis that probability of no exercise would be 0.6. Sporadic, this is sporadic, 0.25, and regular is 0.15. And H1 is H0 is fault. What does H0 is fault? It means that the distribution does not follow the 60, 25, and 15%. So I do the test statistics. It's called chi-square. First, I set my alpha to be 0.05. I do my test statistics to be the summation of all observed minus expected squared over expected. I'll explain it, so not for you not to say, what does this all means? So if for instance, if I say that I have 1,000 students, I expect that 50% would be smoker. I do a test and I get 400. Okay, so what's the difference between 400 and 500? The larger the difference, the more likely that there is a difference between what I expect and what I observe. Okay, so the decision rule first is based on a chi-square with degrees of freedom. K minus 1, 3 minus 1 is 2. I'll show you, just give me a minute. I'll show you the chi-square, how we get this number. So for a degree of freedom 2, كيف Z degrees of freedom 2 أو T and alpha 0.05, the critical, this is called critical chi-square is 5.99. It's similar to the 1.96. Remember that when we set a decision rule, we look at the alpha and then we say that if the Z that we get greater than 1.96 here, the critical is 5.99. So I do my calculation. Here are observed, expected. So this is what I got from the survey after the health promotion. This is what I observed. Yani I went to 470. This is what I observed. So I asked people, do you exercise? Yes, no, sporadically, regularly. I got this distribution. If H0 was true, I would have expected, instead of 255, 282. Where is 282 comes from? If you recall, this is the 0.60 times 470. This is 0.25 times 470, and this is, sorry, so this is one, and this is the 70.5 is 0.15 times 470. Show you again. This is the expected. Expected are the number of student we would have expected to be to do no exercise, to do sporadically exercise or regular exercise under the null hypothesis of 60%, 25%, and 15%. So now I have expected frequencies and I have observed numbers. So these are expected number and these are observed number. I look at the difference between observed and observed and expected. Sorry, and this should have been so for the observed minus expected square over observed. These are the numbers. Is 259. For this one, sorry, they should have been layout ما بعرف ليش صار هيك. So 0.48 and this is 539. So I will write down the formula. So the X bar is 255 minus 282 squared over 282 plus, sorry معلش بكفي هون. This is 125 observed minus 117.5 squared over 117.5 plus 90 minus 70.5 squared over 70.5. This chi-square would be equal to 846. Okay, so this is 8.46. What was the critical value? It was 5.99. So is it greater, less? So since 846 is greater than the critical value at 5.99, remember always the test statistics value, if it's greater than your critical value, this means you reject at 0. So we have this.
Professor?
Yes.
Okay, so we test the statistic for each category, right? And then we add them all together to get the
Yes,
X squared?
yes. It's
Okay.
the summation of all the observed minus expected squared product. So the way this is here, forget about that line. I know it's not clear. So the chi-square is, sorry, chi-square is, here it is, so chi-square is 255 minus 282 squared over 282, 125 minus 117 over 117, 90 minus 70.5 squared over 70.5. All this gives me 8.46. So if I see it on the chi-square, so this is the chi-square, okay. Here is 5.99, which is the chi-square with 0.05 probability. So this is 0 to 1. So if I get a value here, which is 8.46, what would that mean? It will be even less than 0.05. So this is greater than 5.99. And this means that reject the null. So are my observed equal to my expected? If I reject H0.
No, it's greater than.
H0 is H0 was P1.16, sorry, 0.60. P2 0.25, P3 0.15. If I reject H0, what does it mean? That H0 is false. So I don't have this distribution. So when I did my health promotion, I did not get that distribution. So does my data fit this distribution? Does the data
No.
do the data? So this is that's why we call it goodness of fit. So
But
my
Professor?
data do not fit that distribution. It's a different distribution. Because when I look at the difference between observed and expected, the difference is very large. It is more than 599 with the degrees of freedom k minus 1, which is 3 minus 1 equal 2. And this means that the probability is very low. So using table 3 هلا بنشوفها chi-square, the p-value is really very, very low. So this is unlikely that the data fits the distribution. Yes. Go ahead.
Oh, nothing. Never mind. I realized.
I want to show you that the t-test. So I'm going to
Professor,
see. Yes.
I didn't understand how to get the chi-squared.
Yeah, I'm going to do it annotation on my desktop. Okay, so let
Okay.
me remove this.
Doctor, for the degree of difference, it's k minus 1. K is
Yes.
number of what?
It's a number of category and so number of category were none, sporadic, and regular, right?
Ah, okay, yes.
So the number of category of a variable versus, so let me just do, can you give me 1 minute? So I need to go to another presentation to show you the chi-square, to show you the table of the chi-square, and so stop sharing here. Okay, so do you see my screen?
Yes.
Yes.
Okay, so that's the, okay, so I'm not going to be able to annotate, just to show this is the chi-square distribution table. On one side, I have the degrees of freedom. Again, the degrees of freedom are the number of category that makes up a variable. So if the variable is 4 categories, the degrees of freedom, if we're looking at one sample, would be, let's say, in that example, we had 3 categories for the exercise. So the degrees of freedom would be 3 minus 1, it will be 2. So what I was looking for, I was looking at the critical value for a test which has 2 degrees of freedom and 0.5, which is 5%. So this is the 5%. Did you see it? So the first row is the probability. Okay, so this is the 0.05, and this is the 2 degrees of freedom. So this is my critical value. Okay, So the
Okay.
critical value is 5.99. So what we got is 8 point something. So compared to 5.99, it is definitely much larger than 5.99, and therefore it should be less than 0.05. Remember, when we draw, always when we have, let me see if I can draw. I don't know if I can draw here. I don't know how to draw here. No. Anyway, so the chi-square distribution is 5.99. So this is the table. So whenever you want to compare, you find your critical value here. So what did we get? We got an 8 point. So 8 point is somewhere here between 0.025 and 0.01. It means that the probability of my test statistics is much less than 0.05. It lies between 0.025 and 0.01. So that's the chi-square. But I'm going to try one last try to get the PowerPoint. So do you see the okay.
Yeah.
Okay. So at least this one will have all the signs, which is nice. And the one that you will have on your in your Moodle will have all the signs. Okay. So this is the chi-square that I wanted to show you. So it's clear. So this is the H0 is true. So this is the chi-square. On the x-axis are the value of the chi-square. On the y-axis are the probability. As you see, the chi-square is not a normal distribution. We call it a non-parametric. It doesn't at all mimic the normal distribution. But we have a table where we have all the critical value based on the degrees of freedom and the probability. And this is where we can decide what is my critical value, and to decide on, once the test of statistics is done, whether to reject or accept the test of statistics. This is what we've done. I don't know if it's clear. So we said that under H0 that my probability will be equal to 0.60, 0.25, and 0.15. I do my test of statistics. I measure so this is what I got when I got a sample of 470. I got observed value of 255, 125, 90. It doesn't matter what's the proportion, because in chi-square I don't use proportion, but I use the actual value, the actual sample size. So in the expected E are the number of people who I would have expected if they were, if the H0 is true. So 282 is actually 60% of the 470 under H0. 117 is the 25% of the 470 under H0, and the 70.5 is 70.5 persons who would have regular exercise if their probability was 15%. So this is the 15% of 470. The 117 is the 25. The 282 is the 60. So if my H0 is true, I would expect not a big difference between observed and expected. But it's not like this. I have to check it out. So I would look at the difference between 255 and 282, square the difference, and then divide by the expected. And this is the 259. I would find the difference between the sporadic and the expected, the observed and the expected, which is around 80, like 8. I square the 8 over 117, it is 0.48, and 539 is the observed minus expected over expected for the regular. I add all those differences, so all this, for each one, observed minus expected over observed, and the magnitude would turn out to be my chi-square. So this is my chi-square calculated. So the chi-square that is critical is 5.99. I compare my calculated chi-square to my critical chi-square. If it is bigger, this means that there is no evidence of, so my data does not support H0, it means that my data does not follow the 60, 25, 10%, which is, so my data does not fit H0 distribution, and therefore it is different. So therefore we say that we have statistically significant evidence at alpha 0.05 to say that the distribution of exercise is not 60, 25, and 15. This is what we call a chi-square for the goodness of fit test.
Professor, can you
But I
re-explain
want
how
to
to
show
get
you
the
something
calculated?
else.
Okay.
Sorry. Yes, please.
Can you explain how you got the calculated chi-square?
Yes.
I didn't get it.
Okay. So this, okay, again, صح. So it is one sample. Okay, one sample of n equal 470. So I go collect data on 470 students. I ask every single student to tell me to rate themselves whether they are exercises, sporadic, regular, or non-exercises. Based on the data that I collected, which I observed, I found that 255 of my students, so the first line, O, are what I observed when I collected the data. Now, when
Okay.
I hypothesized, when I set an expectation, I said that if, let's say, the health promotion thing does not work, I would expect whatever I collect data from students on exercise to follow a 60, 25%, 15% distribution, اللي هي H0. This is the H0, P1, meaning that I would expect a 60% none, a 25% sporadic, 15% to be regular. So what do I do with those numbers? Hand numbers. If H0 is true, it means that it follows. It means that out of the 470, I would have expected 60% of the 470 to be non-exercises.
we make the table.
اللي هي 470 times 0.6.
Okay.
I get 282. 470 times 0.25, I get the expected sporadic, and I get 117. But how many I observed?
Wait, ما فهمت.
What I observed, when I collected the data, how many were
125.
sporadic? 125. What would I have expected if it was 25%?
117.
117. Okay, so what you do is you calculate the expected based on the 60, 25, 10%. So they are 282, 117, 70.5. So what we do now, we look at the difference between 255 and 282. We square over 282. 125 over 117, we squared over 117. 90 minus 70, I square over expected. So I'm looking at how large is the difference between what I observed and what I expected.
Okay.
And these are the numbers, 259 for the first one, and the summation of observed minus expected over expected. So we put them for you, 259 plus 0.48 plus 5.39, and we end up with a chi-square, which is my test statistics of 8.46. Every time I compute a test statistics, I compare it to a critical value at 0.05. It means that I allow myself 5% of being wrong. So when the probability of the test is 5% or less, I want to reject H0. When I reject H0, it means that my P1 is not 60, P2 is not 25 anymore, and P3 are not, and so I don't have that distribution. And as a matter of fact, the chi-square was 8.46. It was much greater than my critical value at 5%. And therefore, whenever my test statistics is greater than the critical value, I reject H0. Rejecting H0 meaning the distribution is not a 60, 25, 15. So what is the H0 in that example when I have one sample? So the data fits that distribution. Actually, it does not fit the distribution, so I reject H0. Okay? And based on the on the table, actually the p-value is not less than 0.005. I think it's between 0.025 and 0.005 from the chi-square test. Now, let me tell you, the use of the chi-square test is much greater than, or much more frequently used than this kind of example. What we use chi-square test mostly is to compare, is to do 2x2 table. Let me show you if I can do that. So I'm not able to open my PowerPoint. And I think this is related to, because I have updated my computer on Friday, I was told not to restart my computer because I wanted to format all my desktop. So I think I'm not able to use any of the updated program because I did not reboot the system. So I apologize again. So stop sharing. So any questions?